Hi, this is Daniel Carey, and I'm with Team 14, and we're going to talk about multiplexers today. So this is from section 2.9, and so what is a multiplexer? It's a really high-level building block that we don't really look inside at the gates. So we usually draw it as a box, and it'll have a certain number of inputs going into it, and we're going to have a single output going out, and then basically, we have on the left-hand side, these inputs are going to be the candidates for what can actually get passed through to the output. And then we have one input down below that we usually call S, but that'll be the controlling bit or bits that decide which guy gets to get all the way through. So in this example, we have a train that's trying to go through and get to D, but it has multiple trains that are all trying to get to the same spot, and they're all ready to go. So typically we call these I, so it'll be I0, I1, I2, I3. And the control lever down here is like a track controller. So if he puts it on 3, then I3 is going to be able to get through. And the signal on D will be exactly what it was on I3. Okay, so for a 2x1, this means that there's going to be two possible inputs coming in. So up here at the top right, we have the inputs that are coming in there, and then D will be the output. So that's the 2 and the 1. And traditionally, multiplexers only will have one output. So we have an example here of the 2x1. If S0 down here is set to 0, then we see that it chooses the first input for I0, and that's going to get sent to D. And now gate-wise, you'll see that this is the representation of the 2x1, and I'll just use this first one as an example. For 0 coming in for S0, you'll see that it gets passed through to the first AND gate here. We'll draw a 0 there, and then it gets inverted also and goes across into I0's AND gate, so that'd be a 1 there. And then I0, it doesn't really matter what it is because D will end up mirroring what I0 is or I1 is. So let's say I0 is a 1 and I1 is a 0. And we can see that at this first AND gate here, it'll be a 0, 0, so we won't be able to get through, and coming out, that'll be a 0 input there. And then at I0, we'll have a 1 coming in, so we'll get a 1 there, that'll be true. Come out as a 1, and an OR on a 0 and a 1 will be a 1. So we get exactly what I0 was according to our S0 input as 0, so that's what we wanted. Now if we flip it around and we say S0 is equal to 1, then we'll get the path for I1 passing through. So let's set it to 1, and we'll see that S0 gets inverted, and so here we get a 0, here we get sorry, that's wrong. It's a 0 and a 1. And if we just make up a value for I0 and I1, we'll see that 1 comes in, gets ANDed together. So that's going to be a 1 there, and 1 here. And on a 1 and 0 is a 0. So we get 0, and now we get an ORed together, we get a 1 as an output. And so you see that we get exactly what we had for I1, which is what we wanted.
Hi, I'm Vishal Volaboju, and I'll be explaining a 4x1 multiplexer. So a 4x1 multiplexer, it has 4 inputs, and I0, I1, I2, and I3, and it has 2 switches. And to always find out how many switches there are, you can always use this equation, and it has 1 output. So now this is our truth table for our 4x1 multiplexer, and from this truth table we can have this equation over here. So anytime S1 or S0 is 0, then you basically invert it. So now over here S1 and S0 are 0. So over here you have these two inverting symbols, and then over here you have S1, that's 0, and you have S0, that's 1. So this has an inverter, but this doesn't over here. And then over here you have S1, which does have an inverter, and then you have S0, which has the inverter, and the same goes for the last one. You have S1 and S0, which don't have inverters. They're all paired with their selective inputs. So now, based on this equation over here, we can create our we can create our design using logic gates. So now we have S1 that's inverted and S0 that's inverted and I0. So for the first one, they all go through an AND gate. This is I0, and then they have S1 that's inverted. And they have S0 that's inverted. Okay, so that's going to be this over here. And then now we have this equation over here. We have S1 that's inverted. So first of all, this is I1. We have S1 that's inverted. And then we have S0 that's about the same. It's not inverted. And then now we have I2 over here. So here's our I2. And then we have S1 that's non-inverted. So, and then we have S0 that's inverted. We have I2 over there. And finally we have our final equation, which is S1 non-inverted and S0 non-inverted. So this is our I3 over here. This is our S1 that's non-inverted. Then S0 that's also non-inverted. So, and finally, all these go through an AND gate, because essentially each one is going to be something like this. And then they all go through an OR gate because of all the plus signs. That's going to be your output. Now I'm going to explain multiplexers in the real world. So, for example, in a car, you have your infotainment system, and if the driver wants to select temperature, then maybe the input can be 0, 0, and then the infotainment's gonna have like temperature, or if the input's like 0, 1, and then maybe based on the switches and everything else, then the infotainment is going to show miles per gallon. And then if it's like, for example, like 1, 1 and the switch is something, then it's going to show the tire pressure. So yeah, multiplexers are very common in the world of digital electronics.
All right, this is Derek Lindo, and I'm going to be explaining the problem 2.71 over multiplexers. This is designing 8x1 multiplexer using and or not gates. We're going to be looking at I0 through I7 and how we can pass those values for the final output of the multiplexer with the 3 bits S2, S1, and S0. So if we look at I0 first, we see that all of our inputs are 0 from the selectors, which they would all need to be passed through an inverter to become 1. We can see that they do that as it goes through S2, S1, and S0. That changes all 3 values to 1. and going through an AND gate, since they are all 1, it should pass. And the final gate is an OR, so as long as one value is 1, it'll pass through. So D would be I0. Now we can look through at I1. When we look at I1, we see that S2 is 0, S1 is 0, and S0 is 1. So S2 is going to need to go through the inverter to become a 1. S1 is also going to need to go through the inverter to become a 1. And S0 is already 1, so we don't have to worry about inverting that value. And as we get to I1, we see that now all 3 values will be 1. And once again, as it's going through an AND gate, all 3 values are 1, it will output 1, and going to the OR, we just need one value of 1, so this will put out I1. And that's going to be the same repeated step as you go through all the inputs further for I2 through I7. We can see that each 0 will need to go through the inverter to become a 1, because when working with the AND gate, all values will need to be the same to have an output of 1. And if we look lastly at I7, we see that all values are 1, so we never have to go through an inverter. We can just go straight to the AND gate. And that'll give us I7. So this was designing an 8x1 multiplexer using AND or NOT gates. Thank you.